Hey everyone, tonight we're exploring one of the most profound discoveries in all of cosmology, the cosmic microwave background radiation, that ancient whisper from the very dawn of time itself. Before we settle in for this cosmic journey, take a moment to like this. If you enjoy these deep space explorations, and please subscribe if you haven't already. Your support helps us continue these peaceful voyages through the cosmos. Let me know in the comments where you're listening from and what time it is for you. I always find it fascinating how our global community gathers to contemplate the cosmos together, united under the same ancient light that has been traveling to us for nearly 14 billion years. Now get comfortable, dim those lights, and perhaps gaze out at the night sky if you can. Tonight we're not chasing dramatic space battles or alien encounters. Instead, we're going to examine something much more profound and peaceful. The gentle, all-pervading glow that fills every cubic centimeter of space around us, a radiation so ancient that it carries within it the very memory of the universe's first moments of clarity. This is the cosmic microwave background, and it represents nothing less than the afterglow of creation itself. Let's begin our gentle journey into the infinite, following these ancient photons that have been traveling through space since long before our solar system existed, since long before galaxies had fully formed, since the very moment when the universe first became transparent to light. The story of the cosmic microwave background begins not with what we can see, but with what we cannot, the profound darkness that preceded the first light. Picture, if you will, the universe as it existed roughly 380,000 years after the Big Bang. This might seem like an eternity to us, but in cosmic terms, it's barely an instant. A universe still in its infancy, still hot and dense beyond our everyday comprehension. In those early epochs, the universe was filled with a plasma so hot and dense that photons, particles of light, could not travel freely through space. Every time a photon tried to journey from one point to another, it would immediately collide with free electrons, scattering in random directions like a wanderer lost in an impenetrable fog. The universe was opaque, glowing with the fierce heat of its own creation. But that glow could not travel far before being scattered again and again. Imagine this primordial plasma as a vast ocean of charged particles, a sea of protons and electrons moving in constant, chaotic motion. The temperature in those days was around 3,000 Kelvin, hot enough to melt copper, hot enough to vaporize most substances we know. The entire universe glowed with this intense heat, but it was a glow that could not escape, trapped within the dense medium of free electrons that filled all of space. This was a universe unlike anything we can directly observe today. There were no stars yet, no galaxies, no planets, just this uniform, glowing plasma, stretching in all directions. The density was about 1,000 times greater than the density of air at sea level, yet this plasma filled the entire observable universe. It was a cosmos in its most primitive state, governed by simple physical laws, but too dense and too hot for complex structures to form. The photons in this early universe were not the gentle, cool microwave radiation we detect today. They were high-energy gamma rays and X-rays, carrying enormous amounts of energy as they bounced from electron to electron in an endless dance of scattering. These photons were in thermal equilibrium with the matter around them, constantly being absorbed and re-emitted, their energy distribution following the characteristic pattern of blackbody radiation at 3,000 Kelvin. But as the universe expanded, it cooled, And with that cooling came one of the most significant transitions in cosmic history. The expansion of space itself caused the temperature to drop steadily, following the inverse relationship between cosmic scale and temperature that governs the evolution of the universe. As the universe grew larger, it became cooler. And as it became cooler, the violent interactions between photons and electrons began to weaken. The critical moment came when temperatures dropped below that magic threshold of about 3,000 Kelvin. At this temperature, something beautiful and profound occurred. Electrons began to combine with protons to form the first neutral hydrogen atoms. This process, known as recombination, marks the moment when the universe became transparent to light for the first time. It's a curious name, recombination, because these electrons and protons had never been combined before. They had existed as separate particles since the universe's first moments. But the term has stuck, perhaps because it captures the sense of reunion, of things finding their proper place in the cosmic order. The process was not instantaneous, but occurred over a period of roughly 100,000 years, as the universe gradually cooled through the critical temperature range. As recombination swept through the universe, the cosmic plasma gradually transformed into a gas of neutral atoms. The free electrons that had been scattering photons so effectively began to disappear, bound up in neutral hydrogen and helium atoms. With fewer free electrons to scatter photons, light could suddenly travel freely through the space. The universe, which had been opaque and glowing like the surface of a star, suddenly became transparent. This transition was not uniform throughout the universe. Different regions experienced recombination at slightly different times, depending on their local density and temperature. Regions that were slightly denser recombined later, while regions that were slightly less dense recombined earlier. These subtle variations would leave their imprint in the cosmic microwave background, creating the tiny temperature fluctuations that we observe today. The moment of recombination represents a fundamental phase transition in the evolution of the universe, comparable to the way water vapor condenses into droplets when cooled below its condensation point. Just as fog clears when water vapor condenses, the cosmic fog of free electrons cleared when they combined with protons to form neutral atoms. For the first time since the universe's earliest moments, photons could travel unimpeded across vast distances. This moment, occurring roughly 380,000 years after the Big Bang, is often called the last scattering surface because it represents the last time most photons in the universe were scattered by free electrons. From our perspective, looking back through time, this surface appears as a sphere surrounding us at a distance of about 46 billion light-years, the edge of the observable universe. But this is not a physical surface in any conventional sense. Rather, it's a moment in time, a transition that occurred everywhere in the universe simultaneously. The photons released during recombination began their long journey through space, and they've been traveling ever since. When they were first released, they carried the thermal signature of the 3,000 Kelvin plasma from which they emerged. They glowed with the warm orange-red light of hot gas, similar to the glow of heated metal in a forge or the surface of a cool star. This was the first light that could travel freely through the universe, the cosmic dawn, breaking after eons of opacity. But as these photons traveled through the expanding universe, something remarkable happened to them. The expansion of space itself began to stretch these photons, increasing their wavelengths and decreasing their energy. This process, known as cosmological redshift, gradually transformed the visible light of recombination into longer and longer wavelengths. The photons themselves didn't change. They remained the same particles they had always been, but the metric of space through which they traveled was constantly expanding. Over millions of years, that warm orange glow was stretched into infrared radiation. Over hundreds of millions of years, it was stretched further into far infrared. Over billions of years, it was stretched into microwaves, becoming cooler and cooler as the universe itself grew larger and more diffuse. The relationship between the expansion of the universe and the cooling of this radiation follows a precise mathematical relationship. As the universe doubles in size, the temperature of the cosmic microwave background drops by half. Today, nearly 13.8 billion years after recombination, these ancient photons reach us as microwave radiation with a temperature of just 2.725 Kelvin, barely above absolute zero. They carry within them the thermal memory of the universe's first moments of transparency, cooled by eons of cosmic expansion, but still present, still detectable, still whispering the secrets of the early cosmos to anyone with the proper instruments to listen. The cosmic microwave background radiation permeates all of space with remarkable uniformity. No matter which direction we look, we find this ancient glow at nearly the same temperature, varying by only tiny fractions of a degree. This uniformity tells us something profound about the early universe. It was remarkably smooth and homogeneous on large scales, with only the subtlest variations in density and temperature. The isotropy of the cosmic microwave background was initially puzzling to cosmologists. How could regions of the universe that were separated by vast distances, regions that had never been in causal contact with each other, have achieved such similar temperatures? The answer lies in the theory of cosmic inflation, which proposes that the universe underwent a brief period of exponential expansion in its first fraction of a second, stretching regions that were once in thermal equilibrium to cosmic scales. But the cosmic microwave background is not perfectly uniform. Embedded within its gentle glow are tiny variations in temperature measured in millionths of a degree. These fluctuations are among the most important features of the cosmic microwave background, representing the primordial seeds from which all large-scale structure in the universe would eventually grow. Regions that were slightly denser than average would gravitationally attract more matter, eventually forming the first stars, galaxies, and clusters of galaxies. Regions that were slightly less dense would become the vast cosmic voids that separate these structures. The detection of these minute temperature variations required the development of extraordinary sensitive instruments. Early measurements could only detect the average temperature of the cosmic microwave background, but as technology advanced, astronomers began to probe deeper into its structure. The temperature variations they sought were so small that they required instruments capable of measuring temperature differences equivalent to the heat of a candle flame, as seen from the distance of the moon. The pattern of these temperature fluctuations is not random, but follows specific statistical properties that reflect the physical processes that created them. The fluctuations show characteristic features on different angular scales, corresponding to different physical processes in the early universe. The largest fluctuations correspond to regions that were just beginning to collapse under their own gravity at the time of recombination. Smaller fluctuations correspond to acoustic oscillations in the primordial plasma, sound waves that propagated through the early universe before it became transparent. The study of these minute temperature fluctuations has revolutionized our understanding of cosmology. By mapping the precise pattern of hot and cold spots in the cosmic microwave background, astronomers have been able to determine the age of the universe, its geometry, and the relative amounts of ordinary matter, and dark energy it contains. These measurements have transformed cosmology from a largely speculative field into a precision science. The cosmic microwave background also provides crucial information about the universe's composition. The precise pattern of temperature fluctuations depends on the relative amounts of ordinary matter, and dark energy, as well as their interactions in the early universe. By comparing the observed pattern with theoretical predictions, astronomers have determined that ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and living beings, comprises only about 5% of the universe's total energy content. About 27% of the universe consists of dark matter, a mysterious substance that interacts gravitationally but does not emit, absorb, or reflect light. Dark matter makes its presence known through its gravitational effects on ordinary matter and radiation, including subtle imprints in the cosmic microwave background. The remaining 68% of the universe is composed of dark energy, an even more mysterious component that appears to be accelerating the expansion of space itself. The discovery of the cosmic microwave background was itself a beautiful example of serendipity in scientific research. In 1965, two Bell Labs engineers named Arno Penzias and Robert Wilson were trying to eliminate sources of noise from a sensitive radio antenna they were using for satellite communications. They found a persistent, uniform background signal that seemed to come from all directions in the sky, regardless of where they pointed their antenna or what time of day or year they observed. At first, they thought this might be due to interference from urban radio sources, or perhaps contamination from pigeon droppings in their antenna. They even captured the pigeons and relocated them, then cleaned the antenna thoroughly, scrubbing away what they diplomatically called white dielectric material. But the signal persisted, a steady hiss that filled their receivers no matter where they looked in the sky. The signal they detected corresponded to a temperature of about 3.5 Kelvin, close to the theoretical predictions that had been made decades earlier. Only when they learned of theoretical predictions by Princeton physicists Robert Dicker and James Peebles did they realize they had stumbled upon one of the most significant discoveries in cosmological history. The cosmic microwave background provided the first direct evidence for the Big Bang theory, confirming predictions that had been made decades earlier by George Gamow, Ralph Alpher, and Robert Herman. The discovery transformed our understanding of the universe in fundamental ways. Before the detection of the cosmic microwave background, the Big Bang theory was just one of several competing models for the origin and evolution of the universe. The steady-state theory, which proposed that the universe had always existed in essentially its current form, was equally viable from an observational standpoint. But the cosmic microwave background provided decisive evidence for a universe that had evolved from a hot, dense state. The theoretical predictions for the cosmic microwave background had been made as early as 1948, when Ralph Alpher and Robert Herman calculated that if the universe had emerged from a hot, dense state, it should be filled with the cooled remnant of that primordial fireball. They predicted that this radiation should have a temperature of about 5 Kelvin, remarkably close to the actual value of 2.725 Kelvin measured decades later. Their calculations were based on the physics of Big Bang nucleosynthesis, the process by which the first light elements were created in the early universe. They reasoned that the same hot, dense conditions that produced helium and other light elements should also have produced a background of thermal radiation. As the universe expanded and cooled, this radiation should have been redshifted to longer wavelengths, eventually becoming observable as microwave radiation. The cosmic microwave background represents the most ancient light we can observe, older than any star, older than any galaxy, older than any structure in the universe. These photons have traveled farther and for longer than any other light we can detect, carrying with them the imprint of physical conditions that existed when the universe was less than 1% of its current age. They connect us directly to the earliest moments of cosmic history that we can observe, a time when the universe was radically different from the cosmos we know today. As we contemplate this ancient radiation, we're looking at light that has crossed the entire observable universe, carrying with it the memory of a time when the cosmos was young and simple. The universe of 380,000 years after the Big Bang was a place of remarkable uniformity and simplicity, composed almost entirely of hydrogen and helium, glowing with the gentle warmth of its own creation. The cosmic microwave background also provides us with a unique perspective on our place in the universe. Every cubic centimeter of space around us contains about 400 of these ancient photons, invisible to our eyes but detectable with sensitive instruments. They pass through our bodies constantly, carrying their message from the deep past. In a very real sense, we are immersed in the afterglow of creation, surrounded by the fossilized light of the universe's youth. This radiation has been traveling through space for so long that it has witnessed the entire history of cosmic evolution. When these photons were released, there were no stars, no planets, no complex atoms heavier than lithium. The universe was a simple place, composed almost entirely of hydrogen and helium, illuminated only by the fading glow of its own creation. These photons have watched as the first stars formed and died, as galaxies assembled and evolved, as solar systems emerged and planets took shape. The journey of these photons through cosmic time is a meditation on the vastness of space and time. They have traveled distances so great that light from the nearest star beyond our sun has had time to make the round trip to Earth millions of times while they've been in transit. They have witnessed the formation and destruction of countless stellar generations, the birth and death of galaxies, the slow dance of cosmic evolution playing out across billions of years. The cosmic microwave background photons have seen the universe transform from a simple, uniform state to the complex, structured cosmos we observe today. They have watched as tiny density fluctuations grew under the influence of gravity, as the first gas clouds began to collapse, as the first stars ignited in the primordial darkness. They have observed the birth of the first galaxies, the formation of the first planetary systems, the emergence of the cosmic web of structure that spans the observable universe. As we study the cosmic microwave background, we're engaging in a form of cosmic archaeology, piecing together the story of the universe from the faint traces left by its earliest moments. The tiny temperature variations in this radiation encode information about the primordial fluctuations that would eventually give rise to all the structure we see around us. In the seemingly random pattern of hot and cold spots, we can read the blueprint for everything that would follow: the seeds of galaxies, the precursors of stars, the foundations upon which the entire cosmic web would be built. The cosmic microwave background also reveals the fundamental simplicity underlying the apparent complexity of the universe. Despite containing within it the potential for all future cosmic evolution, the early universe was remarkably uniform and predictable. The physics governing its behavior was straightforward. The interplay of gravity, electromagnetism, and thermal energy in an expanding space. Yet from this simple beginning arose all the richness and complexity of the cosmos we observe today. This radiation carries with it the memory of the universe's first triumph over chaos and confusion. In the dense, hot plasma of the early cosmos, matter and energy were locked in a fierce struggle, with photons unable to travel freely through the opaque medium. The moment of recombination represents a victory for order over disorder, the first time that light could travel unimpeded through space, carrying information from one region of the universe to another. The cosmic microwave background is also a reminder of the incredible precision and delicate balance that characterizes our universe. The fact that we can detect this radiation at all, nearly 14 billion years after it was emitted, speaks to the remarkable stability of the fundamental laws of physics. These photons have traveled through regions of space filled with matter and energy, past black holes, and through the gravitational fields of countless cosmic structures, yet they still carry the clear signature of their origin. As we lie here contemplating these ancient photons, we can imagine them as messengers from the deep past, carrying news of the universe's youth across the vast expanses of space and time. They have traveled so far and for so long that they've become part of the fabric of space itself, a constant presence that connects every point in the universe to every other point through the shared experience of cosmic evolution. The cosmic microwave background reminds us that the universe has a history, that it has evolved and changed over cosmic time, and that we are part of that ongoing story. We are not separate from the cosmos, but embedded within it, made of the same matter that once filled the early universe, breathing the same space that these ancient photons have traveled through for billions of years. In the gentle uniformity of this radiation, we find a profound source of cosmic tranquility. Unlike the violent, chaotic events that often capture our attention, supernovas, black hole collisions, stellar explosions, the cosmic microwave background represents the peaceful, steady glow of the universe at rest. It is the sound of silence on a cosmic scale, the gentle murmur of space itself, cooled by eons of expansion, but still present, still singing the quiet song of creation. The cosmic microwave background teaches us about the deep connections that bind all things in the universe together. The same physical processes that governed the early cosmos continue to operate today, governing the behavior of matter and energy on scales from the subatomic to the cosmic. The same laws of physics that determined the properties of the primordial plasma also determine the behavior of the stars, planets, and living systems we observe around us. As we prepare to explore even deeper into the mysteries of this cosmic radiation, we can rest in the knowledge that we are surrounded by the evidence of the universe's most ancient history. Every breath we take, every heartbeat, every moment of our existence unfolds within the gentle embrace of this primordial light, connecting us to the deepest roots of cosmic time and space. As we continue our journey through the cosmic microwave background, we find ourselves contemplating not just the radiation itself, but the profound implications it holds for our understanding of the universe's deepest mysteries. These ancient photons carry within them the signatures of physical processes that operated when the cosmos was younger than 1,000,000 years old, processes that set the stage for everything that would follow in the billion-year epic of cosmic evolution. The temperature fluctuations in the cosmic microwave background are so small that they require extraordinary precision to detect and measure. We're talking about variations of just a few millionths of a degree, differences so subtle that they would be completely imperceptible to human senses, yet they encode information about the fundamental nature of reality itself. These tiny variations required the development of some of the most sensitive instruments ever created, spacecraft and telescopes capable of detecting temperature differences smaller than the warmth of a human hand felt from across a football field. The precision required to map these fluctuations pushes the boundaries of human technological capability. The instruments used to study the cosmic microwave background must be cooled to temperatures approaching absolute zero, isolated from terrestrial interference, and calibrated to extraordinary accuracy. They must distinguish between the faint whisper of the cosmic microwave background and the much stronger signals from our own galaxy, our solar system, and even the instruments themselves. The first detailed maps of the cosmic microwave background came from NASA's Cosmic Background Explorer, COBE satellite, launched in 1989. COBE was designed to measure the spectrum and angular distribution of the cosmic microwave background with unprecedented precision. The satellite carried three sophisticated instruments: the differential microwave radiometer, DMR, to map temperature variations across the sky, the far-infrared absolute spectrophotometer, FIRAS, to measure the spectrum of the background radiation, and the diffuse infrared background experiment, DIRB, to study infrared emission from cosmic dust. When the COBE team released their first all-sky map of the cosmic microwave background in 1992, showing tiny temperature variations across the heavens, cosmologist George Smoot famously declared that it was like seeing God. What they had captured was nothing less than the imprint of the primordial quantum fluctuations that would eventually give birth to all the structure in the universe. The map showed variations of about 30 millionths of a degree, tiny ripples in the cosmic background that corresponded to regions of slightly different density in the early universe. These quantum fluctuations originated in the earliest moments of the universe, when space itself was smaller than a proton, and the entire observable cosmos could have fit into a region smaller than an atom. During the period of cosmic inflation, a brief epoch of exponential expansion that occurred in the first fraction of a second after the Big Bang, microscopic quantum variations were stretched to macroscopic scales, creating the seeds of all future cosmic structure. The theory of cosmic inflation was proposed in 1980 by Alan Guth as a solution to several puzzles in Big Bang cosmology. Inflation proposes that the universe underwent a brief period of exponential expansion, driven by a hypothetical scalar field called the inflaton. During this period, the universe expanded by a factor of at least 10 to the 26, stretching quantum fluctuations in the inflaton field to cosmic scales. These fluctuations would later become the density variations that gave rise to the cosmic microwave background fluctuations we observe today. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, provided even more precise measurements of the cosmic microwave background, revealing the universe's fundamental parameters with unprecedented accuracy. They operated for 9 years, mapping the cosmic microwave background with angular resolution of about 0.2 degrees and temperature sensitivity of about 20 millionths of a degree per pixel. The mission produced full-sky maps of the cosmic microwave background in 5 frequency bands, allowing scientists to separate the primordial signal from foreground contamination. These measurements told us that the universe is 13.77 billion years old, with an uncertainty of just 0.4%. They revealed that the universe is composed of about 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. They showed that space itself is geometrically flat, with a curvature parameter consistent with zero within observational uncertainties. They measured the Hubble constant, the current expansion rate of the universe, to an accuracy of about 5%. UMAP also revealed detailed information about the physics of the early universe. The mission confirmed that the primordial fluctuations follow a nearly scale-invariant power spectrum, as predicted by simple models of cosmic inflation. The measurements showed that the fluctuations are predominantly adiabatic, meaning that the fluctuations in different types of matter and energy are correlated in a specific way. These observations provided strong support for the inflationary paradigm and ruled out many alternative theories of structure formation. But perhaps the most remarkable mission to study the cosmic microwave background was the European Space Agency's Planck satellite, which operated from 2009 to 2013. Planck was designed to measure the cosmic microwave background with the highest sensitivity, angular resolution, and frequency coverage ever achieved. The mission carried two instruments: the low-frequency instrument, LFI, operating in 3 frequency bands from 30 to 70 GHz, and the high-frequency instrument, HFI, operating in 6 frequency bands from 100 to 857 GHz. Planck's exquisitely sensitive instruments created the most detailed map of the cosmic microwave background ever produced, revealing temperature variations down to millionths of a degree across the entire sky. The mission's angular resolution was about 5 arc minutes, allowing it to probe fluctuations on scales corresponding to the size of galaxy clusters. The temperature sensitivity was about 2 millionths of a degree per pixel, limited primarily by the fundamental quantum noise of the cosmic microwave background photons themselves. This map represents the most ancient light we can observe, the fossilized glow of the universe's first moments of transparency. The mottled pattern of slightly warmer and cooler regions across the sky tells the story of the primordial density fluctuations that would eventually collapse under their own gravity to form the first stars and galaxies. Every galaxy, every star, every planet in the universe today can trace its origins back to these tiny variations in the cosmic microwave background. The Planck mission refined our knowledge of the universe's parameters to extraordinary precision. It measured the age of the universe to be 13.79999 plus 0.021 billion years, the Hubble constant to be 67.4 plus 0.5 kWm/s MPC, and the matter density to be 31.5 plus 0.9% of the critical density. These measurements represent some of the most precise determinations of fundamental cosmological parameters ever achieved, transforming our understanding of the universe from approximate knowledge to precision science. The cosmic microwave background also provides crucial evidence for the theory of cosmic inflation. According to inflation theory, the universe underwent a brief period of exponential expansion, in its first fraction of a second, growing from subatomic scales to cosmic scales in an instant. This rapid expansion would have stretched quantum fluctuations to macroscopic sizes, creating the temperature variations we observe in the cosmic microwave background today. The predictions of inflation theory match the observations of the cosmic microwave background with remarkable precision. The theory predicts that the temperature fluctuations should follow a specific statistical pattern, with variations on different angular scales related to the physical processes that operated during inflation. The observed pattern matches these predictions almost perfectly, providing strong support for the inflationary model of the early universe. Inflation theory also predicts that the primordial fluctuations should be nearly scale invariant, meaning that fluctuations on different scales should have similar amplitudes. The cosmic microwave background observations confirm this prediction, showing that the fluctuations follow a power law with a spectral index very close to unity. This near-scale invariance is a natural consequence of inflation and would be difficult to explain in alternative theories of structure formation. The cosmic microwave background has also revealed the presence of acoustic oscillations in the early universe, sound waves that propagated through the primordial plasma before recombination. These acoustic waves were driven by the competition between gravity trying to compress the plasma and radiation pressure trying to expand it. The waves created a characteristic pattern of peaks and troughs in the power spectrum of cosmic microwave background fluctuations, corresponding to the fundamental mode and harmonics of the acoustic oscillations. The scale of these acoustic oscillations provides a standard ruler that allows astronomers to measure the geometry and expansion rate of the universe with extraordinary precision. The angular size of the acoustic peaks depends on the distance to the last scattering surface, which in turn depends on the universe's geometry and expansion history. By measuring this angular scale, astronomers can determine whether the universe is flat, curved, or hyperbolic, and constrain the values of fundamental cosmological parameters. The first acoustic peak in the cosmic microwave background power spectrum occurs at an angular scale of about 1 degree, corresponding to the sound horizon at the time of recombination. This scale represents the maximum distance that sound waves could have traveled in the early universe, and it provides a direct measurement of the universe's geometry. The observation that this peak occurs at exactly 1 degree confirms that the universe is spatially flat, as predicted by inflation theory. The cosmic microwave background has also provided evidence for the existence of dark matter, the mysterious substance that makes up about 85% of all matter in the universe. The precise pattern of temperature fluctuations in the cosmic microwave background depends on the relative amounts of ordinary matter and dark matter, as well as their interactions with radiation in the early universe. The observed pattern is consistent with a universe dominated by dark matter, providing independent confirmation of this fundamental component of the cosmic inventory. Dark matter makes its presence known in the cosmic microwave background through subtle effects on the acoustic oscillations. Dark matter does not interact with photons, so it can begin to collapse under its own gravity, even before recombination. This early collapse enhances the gravitational potential wells that drive the acoustic oscillations, leading to specific signatures in the cosmic microwave background power spectrum. The observation of these signatures provides compelling evidence for the existence of dark matter. The cosmic microwave background has also revealed the presence of dark energy, the mysterious component that appears to be accelerating the expansion of the universe. The precise measurements of the cosmic microwave background, combined with observations of distant supernovae and the large-scale structure of the universe, have shown that about 68% of the universe's energy density is in the form of dark energy. This discovery has profound implications for our understanding of fundamental physics and the ultimate fate of the universe. As we contemplate these ancient photons, we're not just looking at the universe's past, we're seeing the foundations of its future. The tiny temperature variations in the cosmic microwave background represent the seeds from which all cosmic structure would grow. Regions that were slightly denser than average would gravitationally attract more matter over time, eventually forming the first stars, then galaxies, then clusters of galaxies. Regions that were slightly less dense would become the vast cosmic voids that separate these structures. The process by which these primordial fluctuations grew into the cosmic web of structure we see today is one of the most beautiful and inevitable consequences of the laws of physics. Gravity, acting over billions of years, amplified the tiny density variations present at recombination, creating a hierarchy of structure that spans scales from individual stars to superclusters of galaxies spanning hundreds of millions of light years. The cosmic microwave background tells us about the fundamental nature of space and time themselves. The fact that this radiation appears nearly identical in all directions tells us that the universe has the same properties everywhere. It's homogeneous and isotropic on large scales. This observation supports the cosmological principle, the assumption that the universe looks the same from every vantage point, at least when viewed on sufficiently large scales. But there are also subtle anomalies in the cosmic microwave background that have puzzled astronomers for decades. Some regions of the sky appear to be slightly cooler than expected, creating features like the cold spot in the direction of the constellation Eridanus. This cold spot is about 70 microkelvin cooler than the surrounding regions and spans about 5 degrees on the sky. Its origin remains a mystery, though it may be related to the presence of an enormous cosmic void in that direction. There are also hints of large-scale asymmetries in the cosmic microwave background that challenge our understanding of the early universe. The southern hemisphere appears to be slightly warmer than the northern hemisphere, and there are correlations between temperature fluctuations on very large scales that are difficult to explain in standard cosmological models. These anomalies may be due to unknown systematic effects in the observations, or they might represent genuine features of the early universe that we don't yet understand. The study of the cosmic microwave background has also revealed the incredible precision and fine-tuning that characterizes our universe. The physical constants that govern the behavior of matter and energy appear to be set to exactly the values needed to produce a universe capable of forming stars, planets, and ultimately life. If these constants were even slightly different, the universe might have been too hot or too cold, too dense or too diffuse to produce the complex structures we observe today. The cosmic microwave background polarization provides another window into the physics of the early universe. The radiation from the last scattering surface is slightly polarized, with the electric field vectors of the photons preferentially aligned in certain directions. This polarization is created by the scattering of photons off electrons in the presence of temperature and velocity gradients in the primordial plasma. The pattern of polarization encodes information about the density fluctuations and gravitational waves present at the time of recombination. The study of cosmic microwave background polarization has opened new frontiers in cosmology. There are two types of polarization patterns: E modes, which are curl-free and arise from density fluctuations, and B modes, which have a curl and can be produced by gravitational waves from the inflationary epoch. The detection of primordial B-mode polarization would provide direct evidence for cosmic inflation and probe the energy scale of inflation itself. Several experiments are currently searching for these elusive B-mode signals, including ground-based observatories in Antarctica and Chile, as well as balloon-borne experiments. The challenge is enormous. The expected B-mode signal from inflation is about 100 times smaller than the E-mode signal and must be separated from foreground contamination caused by polarized emission from dust and synchrotron radiation in our own galaxy. As we drift deeper into contemplation of this ancient radiation, we can appreciate the remarkable journey that brought us to this moment of understanding. From the first theoretical predictions of a cosmic background radiation to its accidental discovery by two engineers working on satellite communications, from the early crude measurements to today's exquisitely precise maps of the cosmic microwave background, we have gradually learned to read the story written in this ancient light. The cosmic microwave background teaches us about the deep connections that bind all things in the universe together. The same physical processes that governed the early cosmos continue to operate today, governing the behavior of matter and energy on scales from the subatomic to the cosmic. The same laws of physics that determined the properties of the primordial plasma also determine the behavior of the stars, planets, and living systems we observe around us. The radiation we study today has traveled across the entire observable universe, witnessing the slow transformation of the cosmos from a simple, uniform state to the complex, structured universe we inhabit. These photons have seen the birth of the first stars, massive objects that formed from the pristine hydrogen and helium left over from Big Bang nucleosynthesis. They have watched these first stars live and die, enriching the interstellar medium with heavier elements forged in their nuclear cores. The cosmic microwave background photons have observed the gradual assembly of the first galaxies as gravity pulled together vast clouds of gas and dark matter into the luminous structures that would become the building blocks of the cosmic web. They have witnessed the formation of the first planetary systems as rocky worlds coalesced from the debris disks surrounding young stars. They have been silent observers to the emergence of life itself, watching as complex chemistry gave rise to biology on countless worlds throughout the universe. In contemplating this radiation, we are reminded that we are witnesses to one of the most remarkable stories ever told, the story of how the universe evolved from a simple, hot, dense state to the rich, complex cosmos we inhabit today. The cosmic microwave background is the first chapter of that story, the prologue to everything that would follow, preserved in the form of ancient light that continues to bathe us in its gentle glow. The cosmic microwave background also reveals the ultimate fate of the universe. The precise measurements of this radiation have confirmed that the universe is dominated by dark energy, the mysterious force that is accelerating the expansion of space. This discovery tells us that the universe will continue to expand and cool forever, eventually reaching a state of maximum entropy where all matter has been converted to radiation and all black holes have evaporated away. But even in this far future, billions of trillions of years from now, the cosmic microwave background will still be present, though cooled to unimaginably low temperatures. It will remain as a permanent record of the universe's youth, a fossilized memory of the time when the cosmos first became transparent to light. In the deep future, when the last stars have died and the last black holes have evaporated, the cosmic microwave background will still be there, carrying its ancient message across the vast emptiness of space. The temperature of the cosmic microwave background will continue to decrease as the universe expands, following the inverse relationship between cosmic scale and temperature. In 1 trillion years, it will have cooled to less than 1,000th of its current temperature. In 1 quintillion years, it will be cooler still, but it will never disappear entirely, always present as a reminder of the universe's fiery birth. The study of the cosmic microwave background has transformed our understanding of the universe from a collection of scattered observations into a coherent, quantitative picture of cosmic evolution. It has allowed us to measure the universe's age, composition, and fate with unprecedented precision, turning cosmology from a largely speculative field into a mature observational science. The cosmic microwave background has become the Rosetta Stone of cosmology, the key that unlocks the secrets of the universe's deepest past. Modern cosmology rests on 3 pillars of observational evidence: the expansion of the universe discovered by Edwin Hubble, the cosmic abundance of light elements produced during Big Bang nucleosynthesis, and the cosmic microwave background radiation. Of these 3, the cosmic microwave background provides the most direct and detailed information about the early universe, offering a snapshot of cosmic conditions at a specific moment in time. The cosmic microwave background has also inspired new generations of cosmologists and astrophysicists, drawing them into the quest to understand the universe's deepest mysteries. The field of cosmic microwave background research has become one of the most active and productive areas of modern astronomy, with dozens of experiments around the world working to extract ever more precise information from this ancient radiation. Future missions will continue to push the boundaries of cosmic microwave background research. Space-based observatories with even greater sensitivity and resolution are being planned, designed to probe the polarization of the cosmic microwave background and search for the faint signatures of gravitational waves from the inflationary epoch. Ground-based experiments in remote locations like Antarctica and the Atacama Desert will complement these space missions, taking advantage of the dry, stable atmospheric conditions needed for precision measurements. As we begin to drift toward the peaceful embrace of sleep, we can take comfort in the knowledge that we are surrounded by this ancient light, this gentle reminder of the universe's deepest history. The cosmic microwave background is always with us, passing through our bodies, filling every cubic centimeter of space around us, connecting us to the earliest moments of cosmic time. The photons of the cosmic microwave background that reach us today began their journey when the universe was just 380,000 years old, a cosmic infant compared to its current age of 13.8 billion years. They have traveled for so long that entire galaxies have formed, evolved, and died during their journey. They have crossed distances so vast that light from nearby stars has had time to travel back and forth millions of times while they've been in transit. These photons carry within them the memory of a universe unlike anything we can observe today. When they began their journey, the cosmos was 1,000 times smaller than it is now, 1,000 times denser, and 1,000 times hotter. There were no stars, no galaxies, no planets, just a uniform sea of hydrogen and helium atoms, slowly cooling as space itself expanded. The cosmic microwave background connects us to this primordial cosmos in the most direct way possible. We are literally bathed in the afterglow of creation, surrounded by photons that carry the thermal memory of the universe's youth. These photons have traveled across the entire observable universe to reach us, making us witnesses to the most ancient light that can ever be observed. In the end, the cosmic microwave background teaches us about the fundamental interconnectedness of all things in the universe. We are not separate from the cosmos, but part of it, made of the same matter that once filled the early universe, breathing the same space that these ancient photons have traveled through for billions of years. We are witnesses to one of the most remarkable stories ever told. The story of how the universe evolved from a simple, hot, dense state to the rich, complex cosmos we inhabit today. The cosmic microwave background is more than just ancient radiation. It is the universe's gift to us, the preserved memory of its youth, the fossilized light of creation itself. It connects every point in space to every other point through the shared experience of cosmic evolution, reminding us that we are all children of the same cosmic beginning. As you settle into sleep, imagine yourself floating gently through the cosmic microwave background, surrounded by these ancient photons that have traveled so far and for so long to reach you. Feel their gentle presence, not the heat of their origin, but the cooled whisper of their long journey through space and time. Let their uniform glow remind you of the deep peace that underlies all of cosmic evolution, the steady, patient unfolding of the universe's greatest story. Picture these photons as they were when they began their journey nearly 14 billion years ago, glowing with the orange-red light of the hot plasma from which they emerged. They carried within them the memory of the universe's first moments of clarity, the instant when the cosmos became transparent and light could travel freely through space for the first time. Follow them as they journey through the expanding cosmos, their wavelengths stretching as space itself grows larger, their energy cooling as the universe becomes more diffuse. Imagine the vast scales of space and time that these photons have crossed, distances so great that they dwarf all human comprehension. They have traveled for so long that entire civilizations could have risen and fallen billions of times during their journey. They have witnessed the slow dance of cosmic evolution, the patient work of gravity as it assembled the first structures from the primordial soup of matter and energy. As you drift deeper into sleep, let the cosmic microwave background become your cosmic lullaby, the gentle hum of ancient photons singing the quiet song of cosmic evolution. Let their uniform glow remind you of the profound order that underlies the apparent chaos of the universe, the way that simple physical laws, operating over vast scales of space and time, have given rise to all the complexity and beauty we observe around us. Feel yourself becoming one with this ancient radiation, your consciousness expanding to encompass the entire observable universe. You are floating in a sea of photons that have traveled across cosmic time to reach this moment, connecting you to the deepest roots of cosmic history. You are part of the universe, contemplating itself, a brief but precious moment of awareness in the vast unfolding of space and time. Rest now in the knowledge that the cosmic microwave background will continue its gentle journey through space and time, carrying its ancient message to future generations of cosmic explorers. Long after our sun has died, long after our galaxy has merged with Andromeda, long after the last stars have burned out, these photons will still be traveling through space, carrying the memory of the universe's youth. In its uniform glow, we find not just the history of the universe, but the promise of its future, the ongoing story of cosmic evolution that began with the first light and will continue until the very end of time. The cosmic microwave background is the universe's most ancient gift to us, a permanent reminder of our cosmic origins and our deep connection to the fundamental forces that shaped the cosmos. Sleep well, knowing that you are cradled in the gentle embrace of this primordial light, forever connected to the ancient moment when the universe first became transparent and light began its eternal journey through space. You are part of the cosmic story, a child of the stars, drifting peacefully through the ancient light that surrounds us all. The cosmic microwave background is always with you, a gentle reminder of the beauty and wonder of the universe we call home.